Here's a problem where we take our equivalence calculations one step further. We've got a frame which is loaded by a sequence of forces and moments, and what we want to do is identify a single resultant force on this structure and find out where that force acts. What we're going to do here is we're going to make sure that that force actually also takes care of the resultant moment. So we've done some equivalence problems in the past with both forces and moments, and this one asks us to resolve that equivalence package into a single equivalent force. And so we'll explore how to do that here through this problem. Let's write an approach. Step one is we're going to do what we usually do in these equivalent problems, and that is to find the force resultant. Step two is usually the step two in these kinds of problems, which is to find the moment resultant. Step three is the new step for this kind of problem, and what we need to do is resolve these into a single force and figure out where that force acts. So all the action in this problem really takes place in step three. So when we get to step three, we're going to be writing some equations and drawing a nice picture to kind of illustrate how this all goes together. Let's start by defining a coordinate system. So I'm going to define a system like this, which is x and y. And so I'm going to be able to define my forces and the moment in terms of the I and the j and the k coordinate system that we've just defined. Let's start on this page by defining some forces. So what we're going to do here is we're going to find the force resultant Fr. That force resultant is going to be the vector sum of the four forces that are shown there. So the first thing we need to do is to go ahead and define those forces. So let me define them this way. Let me call this one F1, and this one F2, and this one F3, and this one F4. And if we do that, we can write in a pretty convenient way minus 300 in the J, F2 is minus 200 in the J, F3 is minus 400 in the J, and F4 is minus 200 in the I. These things all have units of pounds. So when we put them all together, Fr is then the vector sum F1 plus F2 plus F3 plus F4, and when we add that all up, that just turns out to be minus 200 in the I direction minus 900 in the J direction, and that's got units of pounds. So that was easy enough to do. Now the second part of the problem is to find the moment resultant. And there's a little bit more to this. Let's go back to the original figure. We have to pick a point around which to sum the moments, and I'm going to pick this point right here. I'm going to pick point A. There's two good reasons for that. One is that the question asks us to find the force, the single resultant force, with respect to point A. So I'm going to go ahead and use that as my point of reference. The other thing that does is it allows me to get rid of the moment arm associated with the force F1. So there's really going to be no moment produced around point A by the force F1, and so it simplifies the calculation just a little bit. Let me also point out here in red the kinds of moment arms we're going to see for some of these other forces. So for example, here for F2, we'll see an R2 which looks like that. We'll see an R3 which looks like that. And we'll see an R4 which looks like that. Okay, and we're going to write those in sequence as we go through the solution. All right, let's go ahead and write those. Well, we know M1 is going to be 0 because, as we just established, R1 is equal to 0. M2 is going to be an R cross F calculation. R2 is just 3 in the I direction. We're going to cross that with minus 200 in the J direction. So we get minus 600 in the K direction. That's got units of pound feet. M3 we've got an r of 7 in the I direction. That's going to be crossed with minus 400 in the j direction, so we just get minus 2800 in the k direction, again units of pound-feet. M4, this is going to have an R4 of 7 in the I direction minus 2 in the j direction, and we're going to cross that with minus 200 in the I direction. That's the force. This turns out to be minus 400 in the k direction, again units of pound-feet. And then there's one more moment we have to take care of. Let me go back to the original figure. We have to take care of the moment that is applied at point A. That's going to be M5. And that is in the counterclockwise direction, so that's going to be positive. So if we come over here, we would write this as M5 is equal to positive 600 in the k direction, again units of pound-feet. And so if we do a summation there, MR being M1 plus M2 plus M3 plus M4 plus M5, this just turns out to be MR is minus 3200 in the k direction, pound-feet. Okay. So we've got our resultant force, we've got our resultant moment. Now the question is, how do we resolve those into a single force that acts somewhere that establishes this equivalence condition? All right, so let's go on to step 3, which is to resolve into a single force. What I'd like to do is introduce this sort of idea by drawing a picture. We know that we're looking for a force which acts between A and B on that top member of the structure. So let me just go ahead and draw that top member with A on one end and B on the other. So here's point A. There is point B. And we know that this equivalent force has to have a magnitude of minus 200 in the I and minus 900 in the j, because that's what we solved for in step 2. So let me just sort of pick a point here to illustrate that, and I'm going to do this in blue. Let me pick a point out here somewhere. We've got our resultant force Fr somehow through there like that, and we know that this one, the sort of j component, is minus 900, and we know the I component is minus 200, and the line of action comes through here somehow like that. Okay. Now the reason I intentionally drew it this way, as the I and j components giving us this sum of Fr, is that this gives us a better sort of appreciation for how we can physically calculate the moment and establish this location, this distance from A. So let me draw in red here. Let me illustrate the distance where the line of action intersects line of action of the force intersects member AB, and let me call that distance D. And when we draw it this way, you can see two things. One is that the minus 200 I component of the force doesn't give us any moment around A, because the moment arm is 0. It directly passes through A. And all of the moment around A is tied up in this minus 900 force, which is the j component of this resultant. So we're going to be able to write an equation which is something like the moment around A is equal to d times minus 900. Okay, and you notice that's going to be in the negative k direction, right? So it's minus 900 times the distance d in the k direction, and we know that that has to be equal to that resultant moment right there. So that gives us a basis on which to calculate d. So let me go to the next page and just do that. We know that minus 900 d has to be equal to minus 3200, so that implies that d has to be 3.56 feet. So again, that's measured from A. Okay, let's go back and review what we did here. We have this structure which is loaded by a collection of forces and a single moment, and we want to find the single resultant force which guarantees equivalence of this structure and its loading. And the way we did that was we first found the resultant force, then we found the resultant moment, and the key to the whole thing was the picture that you see on the paper right now, which is this sort of schematic of the line of action of the resultant force Fr with respect to the top member AB of the structure. And when we break it down into components, I and j of the force Fr, it's clear that the moment around O is completely defined by that minus 900j component and the distance d. And the distance d is really what we're really looking for, and so by equating this equation here, right, which we got from the diagram, to what we know the resultant moment has to be, we're able to solve for that distance d is 3.56 feet measured from A.